I like to discuss topics related to infrared photography. In this video, what is preventing your infrared images from being sharp? Even if you're using all the techniques you've learned about digital photography and visible light, some things are different in infrared. In this case, it's diffraction. First, I'll cover some of the basic assumptions about diffraction in visible light digital photography. How do these assumptions impact infrared photography? This involves some physics and math, but don't worry, I'll keep it simple. I've also taken test shots to compare to the math. At the end of the video, I'll provide some practical tips that you can use to make your digital infrared images sharper. So as a landscape photographer shooting in visible light, I needed to understand how the aperture worked. There's a couple basics that we need to cover about the aperture. First of all, the wide apertures have smaller f-stop numbers. Then at the other end of the scale, we have narrow apertures that have large f-stop numbers. When your aperture is wider at a smaller number, it's letting in more light. When it is narrower at a larger f-stop number, it is letting in less light. The other thing that it's having an impact on is depth of field. So at the smaller f-stop numbers, we have a narrower depth of field, and at a larger f-stop numbers, we have more depth of field. So as a landscape photographer, the way that this impacts me is I want a lot of depth of field because I want things to be in focus. So that means I'm going to try to avoid the lower f-stop numbers in my aperture because I want more depth of field. The next thing we need to be aware of is diffraction. So we know that diffraction tends to have an impact on the larger f-stop numbers. So it's the same thing. I want to avoid those larger f-stop numbers because those are going to produce some softness. So what this does is this leaves me with sort of a sweet spot in the middle of the lens where I know I'm going to get the sharpest images because I'm going to avoid the narrow depth of field associated with a small f-stop number, and I'm going to avoid the diffraction associated with a large f-stop number. This is one of the reasons that the saying f8, it's great, came about. But as a landscape photographer, I want even more depth of field, so I'm going to push the sharpness as much as I can. For me, in general, that meant I've always looked at that third largest f-stop number, which is sort of the sweet spot for me for shooting landscapes in visible light. This is just kind of the general guideline that I used when working with new lenses. I didn't, necessarily test every lens. I would just kind of follow this guideline and usually get good results. Then when I started shooting landscapes in infrared, I had the same sort of situation to consider. So this is a different lens and a different range of f-stop numbers. At the low end, we have a narrow depth of field. So we want to avoid the f-stop numbers at the low end of the range. And then we have diffraction at the high end. So we also want to eliminate those because we know that those are going to be a problem. So in this case, I would say, hey, let's shoot at f8 because that's going to be the sweet spot for me shooting infrared. But then I would shoot at f8 and I would find that my images were soft in infrared. And this, was confusing. Why was this happening? Is this more diffraction? In any case, I'll just move over some more. I'll avoid f8 and then I'll shoot at f5.6. For a long time, I just kind of shifted over a stop, but I was still curious about what was causing this and what is diffraction and why are we getting to this place? So diffraction is the property of light that causes it to bend when it passes through an aperture. And of course, an aperture is just like the aperture on a lens. And so how much it bends is the challenge that we're looking at here that we want to solve. So we see light passing through. Most of the light will go straight, but some light will bend as it passes through. And that's the amount we want to figure out, how much of diffraction this is going to cause and how much it's going to make our images soft. One concept that's helpful to understand when thinking about diffraction is this thing called an Airy disk. And an Airy disk is the spot of light, the most precise point of light that you can get that would be captured. Light coming in and hitting the sensor, it will produce this Airy disk. So you have this bright spot in the center that will change in size. And so the smaller the size that is, the less diffraction that we have. And the larger the size of the Airy disk, then the more diffraction that we have. So there's actually a formula that you can use to calculate the size of an Airy disk. And this might look simple to a mathematician, but maybe to a photographer not so much, but it's really not that bad. So let's break it down and talk about the components of this formula. So let's start on the left side of D. What is D? Well, D is the diameter of the first null of the Airy disk. Okay, well, what does that mean? So this is the Airy disk, and the first null is this first dark ring that exists around the center. The diameter of the first null is basically the measurement across. Certainly diffraction is going to create these concentric rings, but the amount of light is not as significant as the size of this central disk. That's the most important thing we want to think about. And why is that important? Because If the size of the Airy disk is smaller than the pixel on your camera, or a group of pixels that are used to collect color, that will result in no diffraction or no visible diffraction in your image. But if the Airy disk is larger than the pixel, then the Airy disk will bleed over into neighboring pixels, and that's what is the cause of diffraction, at least in the photographic sense that we're familiar with. So that's why we're concerned about the size of the Airy disk. The smaller size, smaller than a pixel, no problem, no diffraction. Larger than a pixel, now we have the potential for diffraction and softening of our images. Okay, so we want to take that number. That number is divided by 2 is equal to 1.22 times lambda times n. Whoa, okay, what is lambda? What is n? Okay, well, these are not so bad. Let's take a look at these. So lambda is actually wavelength, at the wavelength of light. And this is something we're actually familiar with in infrared. So a longer wavelength, such as what we have in infrared, is going to equal a larger Airy disk and more diffraction, because anything on this side of the formula that goes up is going to create a larger diameter. N, what is N? Well, there's actually a much simpler way to describe that. That's basically an f-stop. A larger f-stop is going to equal more diffraction. So this formula is really not that complicated when you think about it. Anything on this side of the formula is going to increase the diameter of the Airy disk. So longer wavelengths, the Airy disk goes up. Larger f-stop, it goes up. Wavelength and f-stop are the two things that we concern ourselves with the most when we're thinking about diffraction. So here is a computer-generated Airy disk of white light. And what you'll notice interesting about this is that there's this apparent white spot in the middle, which is, this is actually a little bluish because there's the least amount of diffraction near the blue or violet end of the spectrum. These concentric rings are not just about the amount of light, but they're actually the wavelength of light. You can see it creating a rainbow of color as we extend out because the diffraction varies based on the wavelength. So let's take this formula that we have for diffraction for creating the size of an Airy disk, and let's convert this into terms that a photographer can understand. The diameter of the Airy disk is equal to 2.44. We're taking this divided by 2, and we're going to multiply that on both sides to cancel it out here and double the value here, multiplied by wavelength, multiplied by f-stop. So let's take an example of that. What would that look like? So we'll take 2.44. We're going to multiply that by a wavelength. So let's pick the color green. And let's say we're looking at a green of 525 nanometers. And we want to multiply that by an f-stop. So we'll pick an f-stop of 8, 2.44 times 525 times 8, and that will result in a value of 10,248 nanometers, the actual size of an Airy disk that we could compare to a pixel. We want to convert it to microns because when you start to do research on the internet and look for the size of the pixel size of your sensor, you will typically see that listed in microns, and so that's a little bit easier. A micron is 1,000 nanometers, so if you divide this number by 1,000, you end up with 10.2 microns. So now we can compare this to pixel sizes. So if you looked up the pixel size of your camera, you could actually compare that to this value. So what I want to do now is compare various Airy disk sizes based on a couple dimensions. So based on the a number of wavelengths and then a number of f-stops, so we can see what the results are. So let's take a look at one example. If we're at f4, and we want to look at violet light, so violet light passing through an aperture of f4 at 425 nanometers, violet being at the shorter end of the visible light spectrum, that's going to result in an Airy disk size of about 4.1 microns. If we look at orange light at about 590 nanometers passing through an f4 aperture, then that will result in an Airy disk size of 5.8 microns. And then if we look at near infrared light of about 850 nanometers passing through that same f4 aperture, Airy disk size of 8.3. So what you see here is that when you start at the violet end of the spectrum, you have a certain size of Airy disk. When you move up into visible light and get up to orange, the size of that Airy disk is going to be nearly 50% bigger. And then when you get up to infrared, the size of that Airy disk is going to be double. I'm going to show you the rest of these numbers, but you don't need to worry too much about the numbers. So as we continue in looking at violet light and looking down and go through the various f-stops, the size of the Airy disk is going to increase, and that happens for each of these wavelengths. Furthermore, it's important to notice that when you look at a particular f-stop, the size of the Airy disk is going to increase as you look across the wavelengths. So we start at a short wavelength and work up to a larger wavelength. And what's really interesting about this is that there's actually a pattern that emerges. So let's take a look at an example. If we look at violet light, 425 nanometers, passing through an aperture of f22, that results in an Airy disk size of about 23 microns. If we look at orange light, passing through an aperture size of f16, that produces an Airy disk size of about 23 microns, about the same as violet at f22. And if we look at infrared at f11, so infrared light passing through an f11 aperture, that produces an Airy disk size of about 23 microns. So look at that, it's the same across these. So if we start at violet light, the size of the Airy light disk at f22 is the same, nearly the same, as the size of the disk of orange light passing through f16 is nearly the same as infrared light passing through f11. So you can start to see how the different wavelengths are going to impact your f-stops. These three have the same size of disk. That means they create the same amount of diffraction. So if you're trying to avoid diffraction, you can see how you need to use a lower and lower f-stop as you increase the wavelength, and this pattern continues. So when we look across different wavelengths, you can see this is about 16, 16, 16. As we jump up to the next level, we have 11.5, 11.5, and 11.5. So this pattern continues. Okay, so that's enough math. Let's look at some tests. Some tests that I shot with two sensors, one with a XT2 and one with an XT20. They both have identical sensors. They're APS-C sensors. Your results could vary with different size sensors, bigger or smaller sensors, and different pixel pitches. There's so many variables out there, but this will give you kind of a sense of what we're looking at. Okay, so we're going to start with a visible light test. So this is the XT2 unconverted for visible light. And so I've got some comparisons here. You'll notice that on the left here, we have an F2, and on the right, we have 2.8. So right away, you can see how much of an impact the depth of field is having on this image. The f2.8 image is much sharper than the f2 image. So if I step up to the next level, so 2.8 on the left, f4 on the right, so we can see another jump in sharpness as we go from f2.8 to f4. Compare f4 to f5.6. There's not as much of a change here. I think the f5.6 is a little bit sharper. So now if we go from 5.6 to 8, now we're seeing almost no difference between the two. They're very similar. If we go from f8 to f11, now we're starting to see the effects of diffraction come into play. The f8 is distinctly sharper. There's a little bit of softness happening at f11. And if we look at f11 and f16, now we're really seeing the effects of diffraction. So I started to do the same test with not only with visible light, but I wanted to do this in infrared light. So this first image on the left is 590 nanometers, and then the second image is 720 nanometers, and the third image is 850. And what I began to realize was that the ink wasn't reflecting any infrared light at all. You can see that the fact that it diminishes here is simply the result of less and less of the visible light being captured, and then we get down to this portion of the spectrum where there's almost none being captured at all. So I actually, couldn't use this test chart that I had printed because the ink simply wasn't reflecting any infrared light. So I had to find another subject for shooting, and in this case, I grabbed a book because I figured that Ansel Adams could save the day. So this is a 590 nanometer. And you can see right off the bat at f2, kind of looks like chromatic aberration could be happening here that we're seeing at the very smallest f-stop number. So jumping up from f2.8 to f4, we can see that 2.8 is softer and f4 is a little bit sharper. So now from f4 to f5.6, we're seeing, again, an increase in sharpness. So the f5.6 is sharper than the f4. Now we get to f8, and these are pretty close. So now if we jump up to f8 to f11, now we're starting to see a drop off due to the effects of diffraction. So the f8 is distinctly sharper than the f11. And if we continue from f11 to f16, we can see that trend continuing. Okay, so let's now move on to the next filter I have, which is the 720. We'll jump back to f2 and f2.8. We see that chromatic aberration doesn't exist, but we still have a softer image here at f2, probably because there's less chroma being captured, so there's no chromatic aberration. When we jump from the f2 to the f4, now we're actually seeing a kind of a big jump in sharpness. So we can really see that the f4 is much sharper. When we jump from the f4 to the f5.6, we've got a little bit of a gain. So just a little bit better than f4. So 5.6 is looking pretty good. This is where it starts to get interesting. At 720 nanometers, we're at 5.6, the jump to f8, we're now starting to see the impact of diffraction. So much earlier than we did with this same lens at invisible light or at 590 nanometers. This lens, this sensor lens combination in visible light and in 590 looked great at f8. It looked perfectly sharp at f8, but now that we're up to 720, we're starting to see a little bit of fall off. It's not quite as sharp at f8 it is 5.6, which matches the perception that I was getting before I started this exercise of when I started shifting my shooting to f5.6, because I was noticing this in my images. So if we go from f8 to f11, diffraction trend is going to continue as we get softer and softer. And by f16, we're starting to get quite soft. So this is at 720, and the effects of diffraction are distinctly kicking in earlier. All right, so now let's take a look at 850 nanometers. Starting at f2, we can definitely see it's soft, and we can see an improvement as we go to 2.8. As we jump up from 2.8 to 4, we can see another good sized jump in sharpness. f4 is distinctly sharper than f2.8. And now when we go from f4 to f5.6, now we're actually starting to see the diffraction kick in at 5.6. So this is the 850 nanometer. On the left is f4, and on the right, it's subtle, but you can start to see that the f5.6 is a little bit softer than the f4. So here we're at 850 nanometers, and the diffraction is kicking in 2 stops earlier than it did in visible light. Now, if we continue with 5.6 and 8, we're seeing more softness at f8. And then continuing 8 to 11, the softness continues. And then finally from f11 to f16. Okay, so what are the conclusions that we can draw from both the math and the actual photo tests? Based on the formula, we know that larger f-stop numbers will increase diffraction. So this is something to be aware of. This is going to apply to both visible and infrared light. And we know that longer wavelengths of light will increase diffraction. When it comes to infrared, near infrared, where we tend to do a lot of our shooting, the wavelengths are going to be longer. More infrared, more diffraction. Different lenses are going to create different amounts of diffraction. The size of the pixel is really important, as I mentioned earlier, because you're comparing the pixel size to the Airy disk. So that means that every sensor, every pixel size is going to have different results. The size of the sensor could have an impact. The testing here was done with APS-C. I've read online people who have had different results, who've had more severe impacts of diffraction with micro four thirds and less severe with full frame or medium format. So be aware that there may be variations there. The recommendations I'm creating are intended to create awareness. They're not intended to be like absolute rules. Let's come up with a simplified recommendation for how to deal with the effects of diffraction in your infrared photography. So the simple solution is to avoid diffraction. Use about 1 stop lower from the sharpest f-stop on your lens. That's typically going to be the 4th highest f-stop number on your lens. But again, that's a very general rule if you don't want to dig into the details too much. But if you've paid attention this long, you probably want more specific rules. So at 590 nanometers, remember 590 nanometers is orange and red parts of the visible spectrum plus near infrared light. So at 590 nanometers, diffraction is going to kick in somewhere between 1/3 to 1 stop lower compared to visible light. You're going to want to use 1/3 to 1 stop lower than the sharpest f-stop for your lens. For me, I use a full stop just because I'm trying to avoid the effects of diffraction altogether. When it comes to 720 nanometers, this consists of a sliver of red light plus near infrared light. So diffraction is going to kick in a full stop lower compared to visible light. So you're going to want to use 1 stop lower than the sharpest f-stop on your lens. Now, when it comes to 850 nanometers, this is only near infrared light, which is typically converted to black and white. For these images, the diffraction is going to kick in 2 stops lower compared to visible light. So you're going to want to use an f-stop that is 2 stops lower than the sharpest f-stop on your lens, 2 full stops when you're dealing at 850 nanometers. When it comes to full spectrum, near ultraviolet, all the visible light, near infrared light, the broadest amount of spectrum, and that's going to mean the broadest amount of diffraction that will exist in your images. If you want to be safe, I would still say use 2 full stops from the sharpest spot in your lens, but just be aware that full spectrum means you're going to have the most amount of diffraction. You're going to have very little diffraction in the near ultraviolet part of the spectrum. Probably it's unlikely that you would have any compared to pixel sizes. You're going to have a little bit in visible light and you're going to have the most in near infrared. These are guidelines. This is intended for awareness. There's so many variables here between the sensor sizes and the pixel sizes and the lenses that it's really important that you do some even basic tests. They don't need to be with a chart. You could just find a nice landscape shot, a subject that's not moving, so you can just test sharpness. So test your lenses. Diffraction, it's not all bad. You know, diffraction can be used as a creative choice. High f-stop numbers can produce starbursts, and a soft image could be something that you desire. In talking about diffraction, we want to have awareness of something that could reduce the sharpness of our images, but we're not saying that that's a bad thing. It may be something that you choose to use. So use diffraction or avoid diffraction, whichever you choose, simply be aware that it's going to have an impact on your images. So that's a look at diffraction and its impact on image sharpness for infrared photography. How much diffraction do you see with your camera in infrared? Let us know in the comments below. Do you have any topics related to infrared photography that you'd like to see addressed? Leave a comment below. Do you have any infrared images that you'd like help in editing? There's a link in the description that you can use to send me files. Hope you enjoyed. Thanks.